Hi there. So we have here I have here this another video. This is a supplementary material on week 5 for your general physics 1. So this one deals more on application of Newton's laws. So I'll be discussing, though it is written here already, I will be discussing the problems involved Newton's laws of motion, its application, of course. Okay, so but first we are going to have the concepts. Okay, so in here we are going to have first the application of second law of Newton, those objects whose acceleration is equal to 0. Okay, so or the sum of all forces is equal to 0. So whenever the sum of all forces is equal to 0, this one here, if it is equal to 0, then the system then is said to be in the state of equilibrium. Okay, that is in the state of equilibrium. So there are two conditions when we talk about equilibrium. Okay, so there are two conditions. We have the first condition, which is the summation of forces acting on the system is equal to 0, and the second condition is the summation of all torques. So we are going to individualize this along the process. Okay, so the first condition, so if you're going to take the sum of all forces acting on the system, so you have here along x, then along y, then along z. But in most cases you are going to have the two-dimensional. So we have here x and y axis. So in z, so it will be the higher one. Okay, so that's it. So in this condition, okay, so we must go back to the fundamental equation. So we have here F is equal to ma, but we must note that for the system in the state of equilibrium, acceleration should be equal to 0. So when we talk about acceleration is equal to 0, we have here two things that we can that can be deduced out from it. Okay, so we can say that velocity is equal to 0, so we can say not moving, while on the other one it has constant velocity. So it has constant velocity. So object or system might be moving, but it should not be accelerating, so that the system can be defined to be in a state of equilibrium. Okay, so for the second condition, so we have here torque. So it says that sum of all torque acting on the system is 0. Okay, so with this we have to consider what we call as the clockwise torque. So we have here clockwise torque and the counterclockwise torque. So we have this one. But what is torque then? Okay, so we're going to talk about it later. Okay, so torque. So torque has a symbol of tau. Okay, so torque is equal to R cross F. So when we talk about cross, so cross multiplication, cross, so mean to say that you are multiplying vector. So it should be the resulting product of the multiplication is a vector quantity. Hence, torque is a vector quantity. That is why when we talk about vector, we associate this one to what we call as direction. So you have here direction. So what could be the direction of torque? Well, you have here these two directions. So clockwise torque and counterclockwise, or clockwise counterclockwise. So when we talk about clockwise counterclockwise, so it is related to what we call as rotation. So this involves rotation. Okay, so you have there. So that's it. So we proceed to another part of the information sheet. Okay, so we are going to have the torque first. Okay, so you have here the equation for torque, this one. So you have the equation of torque. Okay, so you have there tau is equal to R cross F. Okay, so the concept of first condition is quite easy because that is second condition, while for the concept of first condition is quite easy relative to the second condition. Okay, so that is why we're going to have this one first. So imagine this is a bar. Of course, in this figure, we imagine this one as a bar or a rigid object. Okay, so at this point here, at this point, okay, at this point it is fixed. It is fixed to a, say, to a wall or whatever it is. So meaning to say that this one at the end is free end. This is free end here. Free. So it can rotate actually. So it has the ability to, it can rotate. Okay. So when will be the object will rotate? Okay. So whenever there is force applied. Okay. So in this illustration, I have here the force. The force is applied perpendicularly to the beam, or say to the bar. Okay, so it will rotate, of course, because there is a force, and because of the force is given on the beam or on the bar or whatever it is, it will rotate in what direction? Okay, that must be in clockwise direction. So with that, there must be what we call as clockwise torque. So this you have here. So by definition above, when we talk about torque, that is basically defined as the force that causes rotational tendencies on the objects. So you have here this force. It is acted upon on the free end of the bar, and of course the bar will rotate, okay, counterclockwise direction with respect to this point. Okay, so you have here this point. Everything, every part of the beam will rotate with respect to this point. Okay, so what is the meaning of this R in here? Okay, what is the meaning of the R? Well, this R here means it refers to the what we call the lever arm. Okay, so that is actually the lever arm. Okay, so notice that the torque is proportional to these two quantities, the lever arm and the force, meaning to say that the force, as you increase the force, okay, this bar here will rotate faster. Okay, it will rotate faster. Now, if this force is of course slower, then of course it will rotate slower. But there is another intervening variable in here, or another variable or factor, that is the lever arm. Now, if I'm going to have the same force, okay, the same force, but the force I'm going to inflict in this part here, it would imply that the bar or the beam will rotate relatively slower. Okay, why? Because the moment arm here now changes. The moment arm become smaller. So with that, we can say that the torque is a function of r and f. So if the f is small, then of course the rotation, well, the rotation of the system will also be slow. Okay, if the r is, say, a large, despite the force, which is say the force is smaller, or yes, smaller, then the system will have to rotate, which is say with maybe the same whenever the force is higher, because we're trying to increase the moment arm. Okay, so as the moment arm increases, of course the torque increases. Whenever there is higher torque, then there will be higher large rotate, or big faster rotation of the system. Okay, so that's it. So there are systems wherein the force and the moment arm are not perpendicular. So in this case here, in this case, they are perpendicular, so there's no problem with that. Okay, so they're perpendicular. However, there are systems wherein the force and the moment arm are not perpendicular. Say for example, this case. Okay, the question here is, can we apply directly the equation? Well, the answer is no, because since this is a cross product quantity, then we have to take into consideration that the force and the moment arm are perpendicular. Okay, so they must be perpendicular with each other. Okay, it should be perpendicular. So they must be perpendicular with each other. Okay, so in this case, in this second illustration, so the force and the moment arm are not perpendicular. So in that case, we have to decompose the force, or take the say the component of the force that is basically perpendicular to the moment arm. So we have here the moment arm. So this is the moment arm, basically our r, and you have here the force. This is the direction of the force. So the force is at certain angle theta, meaning to say that they are not really perpendicular. However, with the use of our trigonometry, we are going to use our trigonometry. Okay, we can actually find the perpendicular force, and this is actually the perpendicular force. Okay, this one. So this perpendicular force actually will cause will create torque on the system. So there is torque in this case because there is perpendicular force, force perpendicular to the moment arm. Okay, so you have there. Now, what about this force here? What is the effect? What is the effect of this force? The Fx. Say this is our Fx. What will be the effect of this force to the system? Okay. Well, it doesn't affect the system. It doesn't cause any rotation on the system. Why? Because, if I'm going to draw this force here, so you have this direction here. Okay, so you have this one. So if I'm going to push this one, of course, this one will not cause any rotation. Why? Because this part here, this force is actually parallel. They are parallel. So with that, it doesn't have any effect, and with that, we cannot define torque. Okay, it defines the definition of torque, that the force and the moment arm should be perpendicular. Okay, so that's it. Now, so in solving for that, well, we should be using actually the sine function. Okay, so we should be using sine function. So that is why you have here this one here. Torque is equal to R perpendicular F sine theta. So you have there. Now, It's not only the force that you can actually decompose into its components so that you will be able to get the perpendicular force in the moment R. But, well, you can actually decompose the R also. Say, I have here. So I have here the R, and I have here the line of action of force. So this is the line of action of force. Okay, so you have here the line of action. Okay, so that line of action actually, say this one. Whoops. So this is the line of action of force. Okay, so you have there. Now, if you're going to imagine this part here, we can actually draw a line from this point. Which can be perpendicular, okay, which can be perpendicular to the line of action of the force. Okay, so you have here. So this one may be defined as our new R. We can actually define this one as to be our new R. Let me use another color. Say I'm going to use blue. Okay, so this can be our new R here. What the? Okay, I hate this. The presentation isn't working, or the PDF is not working fine. So this can be our new R. So this is the R which is perpendicular now to the line of action of force. So you are going to get this. I'm just going to bring it away. Put it somewhere down the road. Okay, so I have here my new R, this part here, but still it's the same. Okay, be it you're going to get a component of the R or the force, they are still the same. Okay, because by virtue of our mathematical rules, so we have commutative properties. Okay, so that it can be, we can apply commutative property in here. So you have there. Okay, so let's go now to the application of the conditions of equilibrium to certain problems that we have. Okay. So this problem is, well, this one is relatively easy because it is only one dimensional. But if it is two dimensional, again, maybe we will be having a hard time. So I'm going to use the red color. Okay, so you have here this problem. So you're going to find a tensional force within a cable that is used to support a hanging object with a mass of 4 kilograms. Okay, so in problem solving, it is very important for us to follow certain format. Okay, and of course, whenever there is problem, we should be able to make a picture of what the problem is all about. Okay, so this is what we call as the diagram or figure. Okay, so you have here, imagine you have here an object, a hanging object with a certain mass. It is supported with a cable. Say the cable is massless. Okay, so there are forces acting on the mass, of course. So this is our object of interest. Okay, so this is our system. Okay, so you have here our system. Okay, so the forces acting on the system, if you're going to look at the figure, so we have here the tensional force, and of course the weight of the object, mass times the gravity. Okay, so there are two forces. You might be asking, what about along the sides? Well, it is hanging, it is swinging. So the object is hanging only, it is swinging. So not swinging. So whenever it is not swinging, then there is no movement along x-axis or along y-axis. It is stationary. If that is stationary, then acceleration is equal to 0. Whenever acceleration is equal to 0, then that is in the state of equilibrium. Okay, so you must be able to qualify as to whether the system is in the state of equilibrium or in the state of, a non-equilibrium state. Okay, so hanging, it is not swinging, therefore this is in the state of equilibrium, and the forces present on the system or acting on the system is basically the tensional force and the weight. And what we are going to do is actually to find the tensional force. What is the tensional force that supports the hanging object in order for the object not to fall downwards? Okay, so that's it. So free body diagram, so you have here, we are now to superimpose the forces acting on the system on the Cartesian coordinate system. Well, there's no problem along x because x axis, the forces is equal to 0. Okay, so and it's actually beyond our interest. What's the interest force that we're going to find is along y. So we have this one. Okay, so when we talk about forces, we should be we should associate ourselves with what we call as force, the Newton's law, particularly the second law. Okay, so the second law states that acceleration is equal to F over m, or we may write this one as F is equal to ma. Okay, that is if you're going to find force. So you have here, but take note that acceleration, okay, so acceleration is equal to 0. So we change the equation of the Newton's law, So you have here, so you have summation of forces along y. We have y subscript because it deals along y-axis only. So we have here along y-axis. There's no x-axis. Okay, it is one-dimensional. So summation of forces along y is equal to 0. So what are forces present? So we have a tensional force, this one, and it's going upward. That is why it is positive. Okay, and then you have your weight going downward. That is why negative. Or basically, it should be written this way, because this is summation, meaning say you are going to add. So you have the tensional force, that is positive, plus you have here the weight, which is going downward, meaning it should be negative, times g, then of course equal to 0 because the system is non-accelerating. Then rule of mathematics, we have time multiplication of signs, positive times negative, so you have here negative. Okay, so we all know that the mass is given. This is equivalent to 4 kilograms, and you have here a g, which is 9.8 meters per second squared. Okay, so if you're going to ask the to find the tension, then you're just going to say rearrange the equation. So take the additive inverse of the weight. Okay, take the additive inverse. So as you take additive inverse of weight, then you will come up with this equation. So this one, the T is equal to m times G. And with that, you have here the working equation. So this is our working equation now. So with that working equation, you can directly substitute the values of the mass and of course the gravitational acceleration. So you have here finally tension, which is equal to 39.2 Newton. Okay, so that's it. That is for the vertical forces or forces along y for a system wherein the acceleration is equal to 0. Okay, so problem number 2. Maybe this is a quite maybe a complicated problem for you, but you shouldn't bother yourselves regarding with this. All you have to do is to practice. Okay, so you have here a problem, an object with a mass of 10 kilogram. With a mass of 10 kilogram is hanging supported by 2 cords. One cord, of course, is supporting horizontally. So we have here this one. So this is basically the figure of the object. So you have here the object. So it is supporting the hanging object. Then another cord is at 60-degree angle with respect to the ceiling. Okay, so you should recall actually your geometry in this case. Okay, so find the tensional force of the 2 cords. Okay, so you have here the 2 cords. It's up to you in how you're going to designate the forces. Okay, so you have here this angle 60, so automatically we may say that using the concept of alternate interior angle. Okay, so this is automatically 16 here. Okay, so in this figure we have here this as tension 1. What's happening? Okay, so you have there tension 1, and of course we have here tensional force number 2, wherein we'll write here as T2. And of course we should not forget the weight of the object, and we have this one as mass times G. Okay, so you have there. So these are actually the forces that is acting on the system. Okay. Okay, so you have here. So going further, we superimpose this one in the Cartesian coordinate system. So we have here this free body diagram. So in this system, it is very important for us to decompose the component of the force, particularly tensional force or tension 2. So you have here the decomposition. So you have here T2 T sub 2x for the x direction, and you have T2 y, that is for the y-axis. What is the purpose of this? So that we will be able to take into account all the forces acting along x and y. So we don't have to bother ourselves with this because we have already these components. Okay, so we have these components. Okay, so that we can apply our condition of equilibrium. Okay, so we have here the first condition actually that will be used. So we have the summation of forces along x, then equate that to 1 to 0, and of course summation of forces along y, then equate that 1 to 0. Okay, because if you're not going to decompose the force, the T2, well, you cannot apply directly the summation of forces along x and of course along y. So now we have here the force along y, and of course x. So I have here the weight, of course. So you have here the component, and you should take into account also the directions. Okay, so you have here the direction of this component of T2, and you have here the component of T2 along y. Actually, this one, this part here, can also be drawn in here. So we can actually draw that one here. So this is your T2 sub y. Anyways, they're just about the same. Okay, so they are just about the same. If you're going to recall on the vectors, okay, drawing of vectors. So you have here. So you're going to add all the forces along x and along y. So what are the forces along x? So you have here T2x going to the positive direction. So you will have a positive T2x. T2x. Then T1 is on negative direction. So that should be minus T1. Then equate that one to 0. You may note this one as a one equation. Okay, so can we find the tensional force using this formula? Well, no, because you have here two unknowns with one equation. Okay, so that is why we have to move forward. Okay, so we have to move forward, and we are going to take the sum of forces along y. So what are the forces along y? So far we have here the weight, and of course we have T2y. So T2y is going upward, so that it should be taken as positive. So T2y, then weight is going downward, that must be taken as negative. So we have T2y minus mg is equal to 0. Okay, then we can actually proceed. Okay, so in this case, if we're going to notice, you have T2y, an unknown, and you have here this variable which are actually given. Okay, so we can advance in our computation. So we have here T2y, which is basically T sine T2 sine 60. Okay, T2 sine 60. So you have here T2 okay, so I have here T2 sine 60 is equal to mg. So I'm just going to divide both sides by sine 60. So sine 60, so that this one will be equal to 1. So we have T2 is equal to mg sine 60. So this is actually our working equation for us to find T2. Okay, so if we have already our T2, and I have T2 here, so I can use this resulting number of T2 and plug it this one here in T2x, because I know that T2x is equal to T2 cosine 60. So you have here T2 cosine 60. So T2 cosine 60 is equal to T1. This is basically T1. Or, yeah. So T1 then is equal to T2 cosine 60. So you have here the relationship. So this is basically an unknown. Okay? And the rule of thumb actually is that do not solve an unknown using another unknown. But in this case, there's no other choice. rather to use this unknown, rather than to use this unknown in order for us to solve this another unknown. Okay, so you have that one. We are using an unknown to solve another unknown. So the computation, so you have here, so that's it. So you have here the composition along x, yes, x and y, then taking the forces x and y, then establishing the equation. So this was the previous equation that we had. So you have here an unknown, another unknown, so two unknowns in one equation, so we cannot solve that equation. Then we have here along y, this is unknown and this is given, so you will be able to, of course, to compute the t2, and you have here the value for t2. Okay, I hope you know how to use your calculators to compute for this. Then using this t2, you can actually compute for t1. Okay, of course you have to use this equation number 1. Just plug in the value of t2. Oops. Just use the value of t2 and plug that one in the equation. Okay, so that's it. So you have that. Just purely substitution. Okay, so your T1 is 56.582. Now, if you're going to go back to the problem, okay, you might be asking which of these two tension chords really supports or have more force supporting this object. Of course, it's very obvious that T2 have greater force compared to this, because T2 is actually supporting the object along Y and of course along X. So you have T2X, then you have T2Y. So you have this support, while T1 is only supporting along X. That is why T2, okay, based on the figure, should have a greater amount of force supporting the object. Okay, so that's it. Now we are going to move forward. We're going to have another problem. Okay, basically this problem is quite easy. Hand tool. So I'm going to use hand tool for me to drag. Okay, so this problem, so you have here an object resting on the table. Okay, so find the force exerted by each force support of the table that is used to support the 10 kilogram mass placed exactly at the center of the tabletop. Okay, so you have here this is your force. You have the force, then another force supporting, okay, the 10 kilograms resting on the floor, table. Okay, so in this case we try to neglect the effect of the mass of the table. Okay, so why do we have to specify that the object is placed at the center? Okay, why should it be at the center? Well, if the object is not at the center, say it is located somewhere here, this force will have to exert more force compared to this one, this set of the other tables. Okay, feet or support of the table. Okay, so that is why if it is exactly at the center, then they will have equal force supporting this object. Okay, so the free body diagram, so you have here this is actually the force supported support, and you have here the weight. Okay, but this one, this Ft here, basically is equal to the sum of the forces exerted by the force support. So we may write this one as Ft is equal to 4 times F's that we have in here. Okay, so it's equal to 4F because there are 4 supports. Then you have here a singular figure representing the entire force that is supporting the mass resting on the table. Okay, so apply the second condition, the first condition, summation of force along x. So you have Ft minus mg. Okay, so that's quite easy. Then Ft, so you have here Ft. Why Ft? Okay, is it Ft? Okay. Why Ft? Yes, that Ft here, I forgot. It means the force referring to table. Okay, it could have been Fs, or the force support. Okay, so there are 4 supports. So going back to the equations that we have here. Okay, so using this one, plug in that one of the equations that we have. Okay, so I missed. So it should have been Fs in here, the supports. Okay, the foot of the table. Okay, so you have here, each support actually gives 24.5 Newton. Each support. Okay, that's it. That is for the problem. Okay, so again, that is a qualified answer to this situation because this is located at the center. However, if this one is located somewhere, okay, in the sidemost or not exactly at the center, then there will be a variation of the supports, the forces of the supports. Okay, so let's move to another another problem. Okay, so you have here a seesaw. Okay, a seesaw. Okay, so I'm pretty sure that you know already what seesaw is. Okay, so you have here a seesaw. So on one arm of the seesaw, a 30-kilogram person is sitting 2 meters away. So you have here a 30-kilogram person from the fulcrum. So okay, so the fulcrum, this part here, this should be our the zero or the origin. Everything will be with respect to the fulcrum, because in here there's no torque. There's no torque. Okay, at the pivot point, the torque is equal to 0. Okay, no matter how big the force that you are going to act at the how do you call this one, at the pivot point, well, it won't cause the pivot point to rotate because the torque is equal to 0. What makes it 0? Well, the moment arm is 0. When a moment arm is 0, then torque is equal to 0. Okay, so you have here. So the figure is already set up. Now, the question here is, find the distance from the pivot point where a 40-kilogram person should sit to balance the system. Okay, so you might be thinking, if you're going to think that, well, that is 40 kilogram, well, he could sit somewhere 2 meters away from the fulcrum. Okay, so well, if you're going to think that way, well, you're wrong. Why? Because 40 kilogram implies that that person have a bigger force or weight. So if you want to balance the system or the seesaw, this 40 kilogram should sit less than 2 meters. Okay, so it should sit less than 2 meters, because if it will sit 2 meters from the fulcrum, well, this one will have to overturn because there is no balance of force. Okay, there's no balance of torque, I mean the torque. Okay, so if it will sit beyond 2 meters, then the more that the torque that the seesaw will rotate, because again the torque counterclockwise and the clockwise torque are is not balanced. Okay, so with that, to maintain the balance of the system, we can actually compute where to put this 40 kilogram person. Okay, so in this case, you're going to apply the conditions of equilibrium, particularly second condition. So the 30 kilogram will cause counterclockwise rotation, so thus it has the counterclockwise torque, and the 40 kilogram person will have to cause a clockwise rotation, thus it will have a clockwise torque. So it should start always this point. This is the condition. So you should start here always. Okay, so summation of torque is equal to 0. What are the torques acting on the system? So we have the summation of torques counterclockwise and of course the torque clockwise. You might be thinking, or you might be asking, why do I have negative sign here? Well, that negative sign denotes opposition of direction. Okay, I usually took the counterclockwise torque to be a positive direction of rotation, while clockwise follows, I assume I treat it to be that one to be negative direction of rotation. What is my basis of this? Well, I just follow the rotation, the quadrantal rotation of the Cartesian coordinate system. Okay, and also the angle. I have quadrant 1, quadrant 2, 3, and of course quadrant 4. Okay, with respect to this positive x, if you're going to have this angle rotation, that is a positive rotation. The otherwise, that becomes negative. So that's my basis. Okay, so it's up to you. You may have this one as positive, you may have this one as negative. Okay, so with that, we can take the additive inverse of this equation, particularly the clockwise torque, so that the system will have to be equal. The clockwise and the counterclockwise will be equal. So plugging in using the formula, so we have a RA cross FA. Okay, these forces here are basically perpendicular to the moment arm. Basically, this one is the moment arm. 2 meter distance is actually the moment arm. So you have here the moment arm R. Okay, so you have here RA cross FA is equal to RB cross FB. This one basically is our unknown. This is our unknown. Okay, so we now take advanced stance. So we have 2 meters plugging in, then x, denote this one as our x. Well, this is quite confusing. Anyways, it is originally from our figure x. So our RB is x. So I'm sorry for that. So I just forgot. Okay, so you have x is equal to 2 meters times the 30 kilograms over 40 kilograms, and as I predicted, or as we predicted, that the person which is 40 kilograms should sit not greater than 2 meters, otherwise it will cause the seesaw to rotate. So at 1.5 meter distance where the 40 kilogram person should sit, it will balance the seesaw. Okay, so we have here. Then another problem. This is quite, I think, this is a bit complicated maybe. So you have here a 2-meter long uniform horizontal beam with a mass of 6 kilograms is fixed on the vertical wall using hinge and supported by a massless cable forming 30 degrees angle with respect to the beam. The cable is fixed on the beam at the distance of 1.5 meters from the hinge. Okay, so the hinge here, the hinge basically is our reference or the pivot. We can have this one as our pivot or whatever. So at the free end of the beam there exists a hanging 5 kilogram mass signboard. Find the tensional force that the cable and the vertical and horizontal support acting on the hinge. Okay, so this is quite long problem, but for me this is quite shorter. But for you this perhaps would be long problem, or yes. The next thing that you're going to do is, of course, to create the figure of the system. So I have here the figure of the system. Okay, so you have here this point, so you have here the hinge. Just check it out if I have a correct spelling. So I have here the hinge, so everything will rotate. Okay, so if I'm going to say remove the cable, this cable, if I'm going to remove this cable, so I'm going to cut this one off, this the mass of the beam and of course the weight at the end of the beam will cause the system or the beam to rotate. However, it won't rotate because I have here this cable supporting the system. Now, say if I'm going to imagine this cable, I can actually take its components. So I have here tensional force along Y. Okay, that is if I'm going to imagine the forces actually that composes this tension of the cord. So I have here Ty, and this Ty, if we're going to go back to what we had, this Ty here will cause rotation. Okay, if we're going to remove this mass, then it will cause rotation. Okay, so that rotation of course will be counterclockwise, while this one will cause a clockwise rotation. Okay, so this problem basically we should be applying the conditions of equilibrium. Okay, why? Because there's a force of the cord that is going to x-axis. Okay, this is a force, this is our Tx. So in reaction to this, according to the third law of Newton, there should be a force counterbalancing that one, that is going to this direction. Okay, let us have this one as my the force of the hinge along what's happening. So this should have okay, so this one, that is the counterbalances the force along x due to the tensional force along x. Okay, so since the hinge is not actually slipping off from the wall, then we could imagine, or we can safely say that there is a force supporting upward. Okay, so there must be a force of hinge, okay, going upward, because if there's no force supporting upward, this hinge here, this part of the beam will have to slip off. Okay, so that's the way how you should be analyzing a system. Okay, so we have here the forces, and of course there is a pre-made free body diagram. So you have there, it's a free body diagram of the system. Okay, so the problem states that the beam is, I think it was 2 meters long. the beam is 2 meters long. Okay, so the beam is 2 meters long, then the weight of the beam should be acting 1 meter. Okay, so it should be 1 meter. Okay, why? Because again, we should take into account the moment arm for the weight of the beam. Since it is uniform, then the weight of the beam should be drawn at the geometric center of the beam. Okay, so that's it. And then this part here, the moment arm is 1.5 meter. Then this one here, you have here 2 meters. That is for the force from the hinge towards the end of the beam. Okay, so the problem is actually quite complicated, but it would take practice for you to master this. Okay, so you have this one. The first condition, we are going to take into account the forces along x and along y. So what are the forces along x? So we have this one, FH. This should have been x. Okay, this should have been x. So it is wronged. So I did this one actually, so it was wronged. Okay. So this should have been FHX. Okay, so and then the TX. These are the forces along x. Then along y, so we have the FHY, the weight of the beam, and the weight of the signboard. I note the weight of the signboard as MS, a mass of the board as MS, and the beam is MB. Okay, so you have there. So for summation force along x, so you have here HX is going to positive direction. Notice, so you have here positive direction, while the TX is going to negative direction. Okay, so you have here this equation, and it's noted to be equation 1. Then what happened? This should have been y. Sorry, this should have been y. So there are a lot of errors. Okay, and there are subscripts. Okay, so along y, so you have upward force, the TH, the HY, and the TY. Okay, so you have here the TY going upward. What goes downward is actually the force of the beam, and of course the weight or the force due to the signboard. This one basically the weight. This is basically the weight. And so with this, these are weights. Okay, so you have that equation there. Equation number 2. So, you know, this one is unknown, this one is unknown, so there's a lot of unknown. Okay, so we cannot just compute directly. That is why if you're going to apply only first condition, you can never solve this one. That is why we have to resort to another condition, that is the second condition of equilibrium, that is the torque. Okay, so the torque, what are the forces that causes torque? So if you're going to go back to the problem, Ty, the MSG, the MBG will cause rotation. Well, how about FHY? Will it cause rotation? Well, the answer is no. Why? Because it is acting exactly at the pivot point. So at pivot, torque is equal to 0 because the moment arm is equal 0. How about the TX? Will it cause rotation? Well, the answer is no. Okay, because the TX is exactly parallel to the beam, so it won't cause any rotation. So parallel forces won't cause rotation, but it will cause basically displacement, and in that case there will be another quantity that we'll be dealing with, and that is the concept of work. Okay, so the forces counterclockwise. Okay, when can we say that Ty will cause counterclockwise, or one will make clockwise direction? Well, we have to define. Say, the axis of rotation, where everything will rotate. And in this case, I choose the hinge to be the pivot point, or everything will rotate with respect to that. So I have here the hinge as the pivot point. So hinge is the pivot. Hinge is pivot. So you have here the hinge as the pivot. Okay, so you have here the RTY. This one will cause a counterclockwise torque, and this should be positive. Then those things that will cause this clockwise torque, we have here the weight of the beam, and of course the weight of the signboard. Okay, so you have your Fs and Fb. Then take the additive inverse. So you have here, then the forces Hy, it will be eliminated. So notice that this tensional force Ty is now can be computed, because the forces and the Rb's and the R's are given. So substituting all the values that we have, you have there that Ty is equivalent to 104.53 Newton. Okay, so Ty, we all know that Ty, if you're going to go back to the illustration, Ty is sine T sine 30. That is why we can directly compute T out from Ty. So you have here T sine 30. So the T is equivalent to 209.06. The unit here should be Newton. Okay. Then for the FHX, the forces, we don't have to use anymore the second condition. Okay. Why? Because we've already found the T. Then given with the equation 1, we can find FHX. So you have there. So that is 181.05 Newton. Okay. So to find the FHY, well, you can just compute or use equation 2. Okay. So you have here FHY is equal to FB plus FS minus TY. TY here, where does it go? Well, basically this negative sign here, it was positive, and this one were actually negative. But when we take the additive inverse using the from the equation 1, then you have here finally. Then finally, HY is going to upwards direction. That is why you will have here 3.27 Newton as HY. You have there. So you have your force HY and HX, then the T. Well, let me go back to the equation. To the figure. If you're going to take a look at this vertical force and the horizontal force, well, the component, the resultant of these two, if we're going to take the sum of this, will be going to this direction, somewhere there. Okay, so this is the force support by the hinge. And of course, even though you cannot see exactly the angle in here, but the resulting force can actually be how do you call this one, can be, the angle can also be reduced out from it. Okay, so you have here, so if you want to compute for the angle here, well, it's up to you. Well, that's all for this presentation. So I hope you learned something regarding with this, because this is quite complicated on your case, but watch more tutorials in YouTube and Khan Academy aside from what I have made. Okay, so that's it. So just take note of the errors. Okay, so just take note of it. Okay, so that's all. I hope you learned something out from this presentation. It's quite long actually.